Hi everyone, welcome to our talk. This paper is titled Comparing the Fidelity of Contemporary Pointing with Controller Interactions and Performance of Personal Space Target Selection, a collaboration between Clemson University, Carleton University, and National Yang Min Chiao Tung University, and I'm Babu. So just a little bit of the background of the problem space. We are talking about on-air interactions with buttons on menu planes and personal space interactions that are very common in VR. And here are some examples. Personal space or near field is the interaction space that exists from the viewpoint to the limits of the operator's maximum arm's reach in VR. And that extends to about a meter or so, depending on the operator's maximum arm reach. And within this space, there are several popular commodity input devices available for personal space interaction. We are looking at the efficacy and speed accuracy trade-off of natural pointing with regards to low fidelity input device, such as the leap motion, which affords low cost, but there are tracking inaccuracies, and high fidelity, which could be like the glove, that are better tracking, but at a much higher cost, and direct controller-based interaction, which are readily available, but not very natural for use, since you're using it as a tool for interaction. Here are some examples of the pointing-based personal space interaction metaphor for menu selection and text area manipulation, and then controller-based personal space interaction techniques in a similar manner. With regards to related work, Tether and Stritzlinger in 2011 actually found that Fitts Law study on different input and interaction techniques in personal space found that haptic feedback was meant to enhance selection performance. Another related study, Lubos, Bruder, and Steinecke in 2014 found that the errors were greater along the viewing axis than along the movement axis when they were selecting targets that were centered at the hip rather than at the eye level or at the shoulder. Our research questions and hypotheses were as follows. We wanted to compare to what extent the efficacy of selection measured by linear relationship between movement time and effective index of difficulty via Fitts Law ISO 9000 standard differed between low fidelity and high fidelity pointing metaphors and controller input in personal space. We also wanted to find out to what extent the accuracy versus speed trade-off as defined by Fitts Law throughput was different between low fidelity, high fidelity pointing, and controller-based input in personal space spatial selection in VR. Our experiment design consists of the following. We varied the depth at which the targets were presented from 60% to 95% of the maximum arm reach, radial distance from 5 centimeters to 10 centimeters, and target width from 0.65 centimeters to 1.05 centimeters. As per the ISO 9241-9 standard of Fitts Law, we measured movement time, the effective user movement distance along the target axis, the over and undershoot of selection at each target location along the movement axis, and the throughput, which was calculated as the index of difficulty, the effective index of difficulty over movement time. The experiment design participants in session were as follows. We had 60% participants in study 1, 60 participants in study 2. The study was between subjects design across 3 conditions. In each of the condition, participant had a total of 702 selections per selection trials. Study 1, 13 trials in each configuration of targets, of target distance by target depth, were presented in the same target plane. And study 2, the target distance by target width targets of 13 targets were presented such that from one target to another, they were presented at random target distances from 60% to 90% of the maximum arm reach. Here's a video of the simulation experience here for the controller condition, in which participants would, in study 1, select 13 targets radially presented via lateral movements in the same depth plane. And once they were completed with these 13 selections, then 13 targets in a different depth plane was presented, and they would continue with their selections. And then in the low fidelity pointing condition, you see that in experiment 1, a similar such design was employed, where the targets were all in the same depth plane for 13 targets. And then after 13 targets were selected, then targets were presented in a different depth plane, in which participants had to select targets by laterally moving their finger. And in experiment 2, participants had to select targets randomly from one depth plane to another within a 13 target configuration of target size and target distance, lateral distance. Okay. So you saw the point LF condition. Now the point HF condition essentially had the same virtual hand metaphor, and the pointer was exactly the same in all three conditions that was used to select the targets. This is the experiment 1 experience, and this is the experiment 2 experience, in which the 13 targets, each of the targets were presented in a 13 target configuration randomly from one target depth to another within the participant's maximum arm reach space. Okay, so the results of study 1, the multiple regression equation was found to be this right here, and this was highly significant with R squared of 0.43. Condition, effective index of difficulty, and target depth were significant predictors of movement time. By condition, we actually found that the controller condition and the point LF condition essentially had the slopes where the point HF condition, the slopes were very similar to one another, with the controller with the point HF condition having a lower slope as compared to the controller, and the point LF condition having a similar slope to that of the controller but at a much higher intercept. And we also found that participants' slopes were significantly different in study 1. So with regards to multiple regression results by the target depth, we found that for the slopes were similar for 75% and 90% of the maximum arm reach, but the slopes was much lower for the 60% of maximum arm reach by target depth of the participants' reaches. Also, the R squared were similar for 60% and 75%, but was different and lower for 90% of the maximum arm reaches. In terms of throughput, we actually found a main effect of condition and target depth. Post hoc pairwise comparisons found that throughput for point LF was significantly lower than controller and point HF. And throughput at 90% of maximum arm reach was also lower as compared to 60% and 75% of maximum arm reach. And throughput overall was highest in the 60% of the maximum arm reaches and lowest at 90% of maximum arm reaches in all three conditions. For study 2, we found a multiple regression equation that was this right here. And this was highly significant. R squared was 0.225. A condition by effective index of difficulty interaction was found to be significant. R squared was 0.26. The slopes for the controller and point HF condition in experiment 2 was very similar, but the slope for the point LF condition was significantly higher, and R squares was found to be similar in all three conditions overall. And we actually found that the slopes were significantly different between the conditions in the participants' linear regression profiles that was found in the results of the study. Also, by studying the target depth, we actually found that similar to study 1, the target depth with the lowest slope was 60% of the maximum arm reach. Slopes increased to 75% and was the highest at 90% of the maximum arm reach. And also the slope for the intercept was the lowest for 60 to 75% of the maximum arm reach, and the slope was more or less at the similar to that of 75 to 90% of the maximum arm reach. But slopes for 60 to 90% of the maximum arm reach was the highest, and the intercept was also very different from 0 for reaches at this distance. Okay, and also a analysis of the slopes and intercepts was found to be significantly different by target depth overall. Okay, when we looked at throughput, we found a main effect of condition and target depth, and we found that overall, when it comes to throughput, the point LF condition was significantly lower than controller and point HF, and throughput for target selection at 60% to 75% of the maximum arm reach was the highest. And also throughput for 60% of the maximum arm reach was highest. And throughput within 90% of the maximum arm reach was the lowest. We also found that throughput for reaches from 60% to 75% was the highest, and throughput at distances from 75 to 90% was the lowest. We actually found that throughput within 60% overall was higher than throughput within 90% of the maximum arm reach. So overall, we found that condition was a significant predictor of movement time. Participants took more time to select targets in the point LF condition as compared to point HF and controller condition. Throughput was higher in the controller and point HF condition as compared to point LF condition. One reason for this is that the point LF condition, the latency and low frame rate could have been detrimental to performance. We also found that target selection within the lateral movements and between depth planes in the center regions of the maximum arm reach in personal space was more efficient and produced higher throughput than selections at the furthest edge of our maximum arm reach. So finally, we found that minimizing latency in popular commodity vision-based gesture tracking systems could improve selection efficacy and speed accuracy trade-off. With regards to menu placement and hierarchical menu placement, placing these menu buttons in depth planes at the middle and of the middle regions of the maximum arm reach was found to be much more efficient, and speed accuracy trade-off was the highest. Future work will focus on raycasting versus pointing versus controller-based target selection in personal space interactions. With that, I thank you for your attention.